All right, get rid of that. Okay, projectile motion. So this first exercise that we're going to do is we have to discover projectile motion using calculus, but let's read through all of this theory stuff in here. A projectile is any object that is thrown or fired up and falls down under acceleration due to gravity. We always neglect air resistance. The path of the projectile is a parabola. When dealing with projectile motion questions, we also consider the time t, which is treated as a parameter because at each time t during the flight, the projectile is at a point which can be measured by an x and a y coordinate. Okay? So that's why we have our x and y Cartesian equation, but t will be a parameter that we'll be using as well. The pronumeral x represents the horizontal distance and y represents the vertical distance. T represents the time. So there is two ways to specify velocity. The velocity of a projectile at some particular time t can be described in two ways. So first of all, we can give the speed and an angle of inclination. The angle of inclination is the acute angle that is between the horizontal path and the angle that we're projecting. If it is positive, then the object is traveling upwards, and negative if it is traveling downwards. Okay, so you've got to have the direction from the vectors in there. Approach 2, we can give the horizontal component, we will be calling that x with a little dot above it. So if you see that notation, that means velocity. Got to find my highlighter in here. So that is another way how we're going to be writing velocity in the horizontal component, and y is our vertical component of velocity. This allows the velocity to be written in vector form. So velocity vector is the velocity of x in I, because I is the horizontal direction, and velocity in the y direction in the vertical for j. And it has them separated there as well, where the velocity of x is v times I and the velocity of y is v times j. The resolution of velocity. To convert between velocity in terms of speed, v, the angular inclination, theta, and velocity given in terms of horizontal and vertical components, the x with a dot and the y dot, use a diagram to resolve the velocity into its horizontal and vertical components. So what that means is we're going to be drawing diagrams, and I always like to draw one. You'll have some projectile coming up here in a parabola, and at the very start, we have, oops, I just deleted that with my funny pen. There we go. At the very start, we have a velocity v and an angle theta. If we're to make that into a right angle triangle, to find the horizontal component of that velocity, we would be using the adjacent side and the hypotenuse, which will be cos. So you could, if you want to do it as a calculation first to see where those formulas come from, you would go, oh my goodness, I keep touching the screen, it keeps moving, sorry. Cos theta equals x over the hypotenuse, so it's adjacent over hypotenuse, x being the x direction. So the x velocity would be v times cos theta, and that's this formula that you have over on the list over there. And you do the same thing for the y direction. But you'll get to the point where you go, well, it's just pretty obvious. If I'm doing the horizontal, it's going to be v cos theta. If I'm doing the vertical, it's going to be v sine theta, and you won't have to work it out every single time. Okay. You can see the velocity one over here. We can use Pythagoras' theorem. So if you know the velocity in the x direction and the velocity in the y direction, Pythagoras' theorem will give you the velocity on that hypotenuse. And tan theta can be, so if you're trying to find the angle of inclination, you might be working backwards. You could simply find the velocity, the opposite over the adjacent. That's just your tan theta for opposite over adjacent, SOHCAHTOA from way back. You can be using that with your velocity in there to find the angle if you need to. All right. So a whole bunch of information, like always, thrown at you, and then I'll show you how it all works. A few more little things down here at the bottom. The fundamental equation of projectile motion. Projectile motion is governed by the acceleration vector, where acceleration is minus the gravity in the J or the Y direction. Acceleration only happens in the vertical plane. There is no acceleration ever horizontally, and you probably know that because you all do physics. Isaac was the one that doesn't do physics, wasn't it? Okay. So in practice, however, we work with the equations for the horizontal component of acceleration. So we would always start with, you can see, I hope you can see where I'm reading from, x with 2 dots above it. 1 dot is velocity, 2 dots is going to mean acceleration. So acceleration in the x direction is always 0. And the vertical component is always going to be negative gravity. Okay, now the thing with maths as opposed to physics is that you have to start from scratch every time with your equations and derive the formulas that you're going to use with your calculus. Okay, we can't be, sorry, what's that? Yeah, they will be very similar each time, but you have to actually show the process. It's a requirement that they say that you have to do it from scratch. You can't just memorize certain rules to use. Yeah.
Negative.
Oh, no, don't do it twice. So if you're saying gravity is 9.8 or 10, so it's just negative 10 because it's always accelerating towards. Okay. Yes, correct. Yeah. So sometimes it depends on the question. It depends on the question. Sometimes, a lot of the time in the textbook, I think they use 10 pretty much all the time. And some questions will say use 9.8. So read the question. It will tell you what it wants you to use for gravity. Unless otherwise indicated, every question in projectile motion should begin with these 2 equations. So you've got to start with those and build the rest of your stuff from there. The working will usually involve 4 integrations. Starting with your acceleration, you'll integrate to get velocity for both of them and integrate again to get your displacement in both directions. There will be 4 corresponding substitutions to find the boundary conditions because, did you do some integration with Mr. Harris yesterday? Yes, good. Okay, yeah. Yeah, yes, it's a bit awkward that you haven't done much integrating yet in your advanced. But when you integrate, remember the family of curves, because when you differentiate, you lose that constant every time, don't you? So when you integrate something, there could have been that constant that in there, and you've got to work out what that could have been. So there's we plus a C in there and work out what that is. That's our boundary condition. All right, so we'll see how we go and what is missing from your advanced content that you don't know yet, but let's have a go of these questions. So question 1, use a diagram to resolve the velocity into its horizontal and vertical components for a projectile moving with speed of 14 meters per second at an angle of inclination of 30 degrees. Give your answer as an expression for the velocity vector, v there, in vector components. So because it's our first question, and I always like to do it anyway, a little diagram always gives you a visual on what is happening. So we have a projectile, which, here's my horizontal ground. It is being projected up at an angle of 30 degrees. The speed in the question there is 14 meters per second. So even though, yes, if I was to continue, I could draw the rest of my parabola in, but we're only talking about the initial velocity here. So we want to draw a right angle triangle and work out the horizontal and vertical components. So this is our first question, first time, so I'm going to do it slowly, and then you might eventually, like I said, start to shortcut to what the answer should be. So if I'm trying to find my velocity of y and my velocity of x on those ones there, if I'm doing the x first, why not? I would do cos 30, because it's the adjacent and the hypotenuse that I've got there, equals velocity of x adjacent over my hypotenuse, which is 14. Get the velocity of x by itself, so it will be 14 cos 30. Now, exact values. Cos 30 is an exact value. What is the exact value of cos 30? Or do we need a formula sheet? Cos 30, hey, you know what you do? This is what I used to always do. I always used to get confused, and I still do sometimes, between, I know one of them's root 3 over 2 and the other one's a half, between the 30 and the 60 for sine and cos. So if you type in, yeah, I know. So if you type in cos of 30, it's obviously not a half, that's the root 3 over 2. But you've got your formula sheet if you need to as well. Okay, so that is going to be 14 times by root 3 over 2, which means I can divide the 14 by 2 to be 7 root 3. Sorry, but that's not a lot of space in there. Okay, now let's do the same thing for the y direction. So that was my x. Let's do our y up here. So that's going to be opposite end hypotenuse. So I'm using sine. Sine 30 equals opposite is velocity of y over hypotenuse, which is 14.
Right, how do you
I'm just using Sokotoa, or you're talking about my exact value?
Yeah.
I've done these exact values so many times. I know for the 30 degrees, it's either going to be half or root 3 over 2. Or you've got the triangles. Yeah, that's what I'm saying. You get your formula sheet out and just use the triangle.
Yeah.
Times the 14 across the other side, so it'll be 14 times sine 30. So exact value of sine 30 is, what did you say, sorry? From the triangles, it's, nope, a half. So it's 14 times a half, which I'm going to write that because I'm running out of room. It will be 7. And these are actually meters per second. They're velocities. Okay. So I have found the velocity in the horizontal and the vertical components. How can I write that in vector form? So in the question, it told me to use vector v. So my velocity in the x direction was 7 root 3, and we call it I, plus y direction would be 7j. That wasn't so bad, was it? And you will find that you will shortcut those first parts down quite a bit quite quickly because they will get repetitive. Part B. Use a diagram to resolve the velocity into its horizontal and vertical components for a projectile moving with 14 meters per second at an angle of inclination of minus 30 degrees. Give your answer as an expression in the velocity vector, in vector components. So very similar. All I'm changing. Yes. Oh, it doesn't actually matter, but we usually put a second. Yes. Has to. Okay. All right, so let's draw it though to see what we're doing. This time, it's very similar to the last question. There's my horizontal ground, so there's going to be my velocity of my x going that direction. But this time my angle is negative, so it's going to be 30 degrees down. Now, I'm not going to put a negative 30 there, but it does mean that the y component of my velocity is going to be negative, doesn't it? So it's going down. It's still 14 on the hypotenuse, meters per second. So let's go through again the x velocity. To find it, it's the same question as before. So if I'm finding that, it is going to be 14 cos 30 again, which is, I've already calculated this in the last question, so that's 7 root 3. We did that before. And the only difference is my y velocity. I just have to make it a negative 14 sine 30, or you could go straight to negative 7 because we've done that calculation before. Yeah, same numbers, just negative on that y direction because we're going down instead of up. It's the only difference. So to write it in vector form, v equals 7 root 3 I and minus 7j.
Oh,
Question 2. You done question? Is that question 2? You're telling me an answer? Oh yes, we will. Yes, correct. All right, I haven't even read it yet. Find the speed v and the angle of inclination theta, correct to the nearest degree, of a projectile whose velocity vector is v equals 3I plus 4j meters per second. Yeah, so keeping with my theory of drawing a diagram. So the x component of velocity is the 3 and the y is the 4. So like Ben said, if I need to find the hypotenuse, I would simply use Pythagoras' theorem to find the velocity across there. Yes. So you may have that one memorized. We sure will have that memorized, but we're just doing 3 squared plus 4 squared. So my velocity is going to be 5 meters per second. But that is not all we had to find. It said to find the speed v and the angle of inclination. So one of the formulas that was on that previous page was I can find the angle of inclination with tan theta equals velocity of y over velocity of x. In other words, opposite over adjacent. So yep, so it's 4 over 3. And say yes to the nearest degree. So you just grab your calculator and you'll inverse tan that and round it to the nearest degree. And Senny's got the answer. Yeah, good. 53 degrees. All good? Easy, easy, keep going. Part B. Find the speed and the angle of inclination theta to the nearest degree of a projectile whose velocity vector is v equals 7I minus 2j meters per second. So very similar question. Let's draw it. So the 7I, so positive, I'm going to put 7 there, sorry. One thing I can't do with this new pen is delete things as easily. There we go, 7. And the negative 2 is telling me that the vertical component is going down. So that's velocity is negative 2 going down that way. So my angle is going to be beneath the horizontal, so it should end up being a negative. So let's find, first of all, our velocity, Pythagoras' theorem. So velocity will be the square root of 7 squared plus minus 2 squared. And that one doesn't come out quite as nice as the last one. Let's leave it in third form. Square root of 53. To find the angle of inclination, we're using tan theta equals opposite over adjacent. So my opposite is 2 over 7. I'm not using the minus sign because I don't want my calculator. Let's just check that. Shift 10. Yeah, but I want the acute angle. I'm just going to see. Does it leave it acute if I leave the minus in there? Let's have a go. Minus. Where's my minus sign? There. Oh, I put the negative in front of it. Yeah, okay, yep, all right, let's put it in. Yeah, as long as you know what your calculator's doing. Yeah, I guess it's fine for tan, because tan's okay. If it was sine, it probably would have given me the obtuse angle, but tan's fine. So that gives me a negative 16 degrees, rounding it to the nearest degree. Right. Okay. Now, those are a couple of little questions. This one over here, when we get to question 3, these are the whole shebang. All right, so what we have is a person standing on the top of a 35-meter cliff. They're going to throw a ball with a velocity of 16 meters per second at an angle of inclination of 30 degrees to the horizontal. Using where the person is standing as the origin, and gravity is 10 meters per second squared, find the 6 equations of motion. Remember, we talked about this 6 because we start with the acceleration, integrate to velocity, integrate both of them through to the displacement. So there's 6 equations that we need to work with here. So these are the big questions where you've got to do all the work, no formulas, show everything via calculus. Okay? All right. So I like to divide my page up so that I have my horizontal component, my x component, I do that all on the left, and then I do my vertical component on the right. So let's do that. I'm going to start on my x side. So we always start on the x. There is no acceleration, so it means it is 0. Acceleration always 0 on the x direction. If I need to get, that's actually your first equation, by the way. That's one of your 6 done. Yeah, so that's an easy one. That's a gift. To get to the velocity equation, never mind. Okay. To go from acceleration to velocity, you need to integrate your acceleration. So I'm integrating 0. Yep.
I mean. Oh yeah, never mind. The horizontal initial velocity should be the same as the final horizontal velocity.
It'll be constant.
Yes.
Velocity is constant in the x direction. But we know that, and you guys know that because you've done lots of physics, but we have to show it. Okay, so integrating 0 means that how do we get 0 when we differentiate? We'd be differentiating a constant, wouldn't we? So when you integrate 0, it goes back to being your constant. So that's going to be constant number 1, because remember there's going to be a few integrations in here, and we can't use c for all of them. So you're meant to call them 1, 2, 3, and 4 for your 4 different constants that we're going to be working out. Okay, now I need to work out what that constant is equal to. So a little bit of work needs to happen up here on my diagram. Now, I've got the numbers on there already, but let's draw our right angle triangle in here so that we can work out our initial velocity in both the x and the y direction. So initially, this one here, let's do the shortcut. If I want to find y dot, it would be the velocity times sine of the angle. Is everyone okay with that? So my velocity is 16 and my angle is 30, so 16 sine 30. Sine of 30 is an exact value, which is half. So it's 16 times a half, which means that is 8 meters per second. All right, the one we need for now is the x velocity. It is going to be the velocity times cos of the angle. So 16 cos 30, and cos 30 is the root 3 over 2. So divide your 16 by 2, it is 8 root 3 meters per second. Okay. So it says that the person, I probably should put that in here as a little note as well. It says the person is standing, the origin is going to be where they're standing, which is there. So that's my point 0, 0. Okay. All right, so back to my integral down here. Initially, when time is equal to 0, that's what initially means for velocity. When time is equal to 0, what is my initial velocity in the x direction? Nope. Look at that, I just worked it out. Diagram. In x direction. Yes. Yeah, not timesing it by 0. So what I'm subbing in here is I'm saying when time equals 0, so the projection of this ball, the speed, velocity, is equal to the 8 root 3 that we worked out from our diagram. So subbing that into my equation there is no t. I'm just getting that my constant is going to be equal to 8 root 3. So as hope you expect, my velocity is equal to 8 root 3 always, because the velocity does not change in the x direction, right? Over time, it's always going to be 8 root 3 the whole way through that parabola. That's my second equation. To get to the third equation, I have to integrate that again. So that will be the displacement of x. I want to integrate 8 root 3 dot dt. We're always integrating with respect to time. How do I integrate a constant? Say it again louder, Ben. C2. Oh yeah, there will be a C2, but what about the 8 root 3? I need to put something else in there. T. Yeah, we're using T instead of X because of time. We're integrating over time. So it's 8 root 3t because you're adding your constant in. So exactly how much integrating have you done? Oh, okay. We did do some last year, like a little bit, like the family stuff. Oh, okay. All right. Okay. All right. Quick go through then. If you're integrating 0, you're going to get a constant. We've gone through that part already. If you are integrating a number, so a number like that, if I'm integrating 5, if let's do it with dx's, because you're going to do dx's when you're doing it in advanced, then it will become 5x. You're adding an x power in. If I was integrating the 5x though, you're reversing the differentiation. When you're differentiating, you bring the power down and you take one off the power. When you're integrating, you add 1 to the power and you divide by the power. Plus c, yeah, got to plus my constant on, so plus my constant on there as well. I've already, that was a new question. Yes, I was just doing 5x, just into 5x. Maybe I should have started a new question there. But yes, if I'd worked out what c was, then yes, I would have had to put a c on there. An extra. No, no. You always have to work out the constant in between before you can do the second integral. Yes. Okay, does that kind of make sense? So integrating is add 1 to the power, divide by the power. Yeah. Yeah, we did. All right, anyway, that's not this question. Let's delete that. Okay, so that's what I had, the 8 root 3, and when I integrated, I had to add in the t because I had 0 t's, so I had to add 1. And I do have to add my plus c2 for my second constant. We always are thinking about what is happening when time equals 0. So when time equals 0, how far have I moved? This is displacement. How far have I been displaced in my x direction? 0, correct. Haven't moved at all. So when time equals 0, x equals 0, so what is c2 equal to? Correct. So looking at that equation, if x equals 0, time equals 0, then that means c2 is equal to 0. So my equation for x is 8 root 3t. Third equation, and I'm done with the x direction.
Wait, how do we know x is 0?
I'm using a starting point as my reference so I can find the constant. Yeah. So x is your yeah, I guess that's one way of thinking of it. Yes. So if we x is our original equation, we often like to start with our x equation, and normally we'd be differentiating to go up to the others. But in this case, we're starting with the acceleration, and we have to integrate to come back to the displacement equation.
So the x dash?
I guess the x dash is the x dot that I've got there, because the derivative of the displacement is velocity. No, we're done. All right, so now we're going to go to the y direction. Y direction, we were told in the question, what are we using for acceleration? Yes, so it'll be negative 10 because we're always accelerating downwards towards the Earth. So acceleration is always negative in the y direction. There's my fourth equation. That's an easy one, see? So I need to find the velocity now, so the y with a dot, which means I need to integrate negative 10 dt. Okay, I'm integrating a constant, so what's it going to become? Yes, Ashton? Yeah, so the question said to use negative 10, so it's just been rounded. Plus c, we're using c3. It's divided by 1 because the powers are 1. Yes, you divide by the new power. Yeah. Okay, to find that constant, I need to sub some things in. Let's look initially, when time equals 0, what is my initial velocity in the y direction? Look back to the diagram at the top. Yes, 8. So subbing that in, I would get 8 equals minus 10 times 0. You can sub all this stuff in if you need to see it, plus the c3, that's just 0. So what's c3 equal to? 8. So my equation for velocity is minus 10t plus 8. Second last equation, got one more to go. Last equation is to get to the displacement for y, which means I need to integrate that equation, negative 10t plus 8, in terms of time. Integrating, we're practicing. So I've got minus 10t. Add 1 to the power becomes t squared and divided by 2. So you could just go straight to -5, but I thought we needed the practice with integrating. The 8, because it's a constant, it's going to become an 8t. And I will need to add another constant, which will be C4 to the end of that. Okay, then I need to sub some things in to find that constant. Actually, I'll rewrite it first because I want it to be -5. -5t, because I added 1 to the power, it became a t squared. So because the power was a 2, I had to divide by 2. So add 1 to the power, divide by the power. Remember that?
Yeah.
So initially, and think carefully here, when time is equal to 0, how far have we been displaced vertically? Y is equal to?
Oh, this is B equals U. No, S equals.
It is kind of, but we're not allowed to use those. No, that doesn't exist.
Can you scroll down a second?
No, because I need you to see here. I will go back in a minute. That's why I had to make a note of where the origin was being placed. Sometimes, if you were just left to choose, you could choose whether the origin was at ground level or if the origin was where they were shooting from. The question said that that the origin had to be where they were standing, which is at the top of that cliff. Which means initially, they have not moved at all, vertically or horizontally. So y would be equal to 0 as well. But it does mean that where they land, they're going to be landing negative 35 meters below the origin. Okay, so it's all about where we place that origin to start with, and it can vary. Okay, so for this one, when time is equal to 0, our y is equal to 0. And that means that -5 times 0, that's 0. 8 times 0 is 0. So what is C4? 0. So y equals -5t squared plus 8t.
Or you go Y equals 8t.
Are you still trying to use those formulas? Yes, using your formulas. Okay, part B. Now we want to do some things from those. We've derived our 6 equations. Now we have to do some calculations based on them, I think, in part B. Let's have a look. Find how high the ball rises, how long it takes to get there, and what its speed is then, how far it is horizontally from where it was thrown. Okay.
You use the.
Yes, very good. If I want to know how high the ball rises, and this is where your physics stuff is really going to help you guys. When you think of a projectile, when the ball is coming up, it comes up, and there's that moment where its vertical velocity is 0, and that's when it comes back down. So if you ever want to know how high something goes, you make the velocity in the y direction equal to 0. Okay, so when y dot equals 0, and our equation for y dot, I'm going to have to flick back to the other page. It was -10t plus 8 equals 0. So we just want to find t. Yes. So 10t equals 8 divided by 10, we get 0.8 seconds. Okay, that tells me the time it takes for it to get there. I think we're going to run out of time. Phil's about to go. To find the height, because it says how high does it rise, I have to sub that into something. Where should I sub it? Yeah, the equation for y. So I'm going to sub when t equals 0.8 into y. So that's going to be y equals -5 times 0.8 squared plus 8 times 0.5. 0.8, sorry, thank you. 3.2. That is actually how high it has been raised from the starting point. If you wanted to know how high it was above the ground, what would you have to do? You'd have to add the 35 on there. So therefore, 3.2 plus 35 means it's 38.2 above the ground.
All right.
Yes, it is.